In the past 3 episodes, we've fiddled around with electronics and software in order to custom build a simple engine control system that will allow our tiny supercharged diesel engine that we're using in our test car to operate in an urban environment without belching a dark cloud of smoke every time it accelerates. The goal is to move our testing from the back roads of rural Kansas to the big city, and see if this car can compete in normal traffic. Now, in order to conceal the fact that this car is powered by a tiny diesel engine that's normally found in mobile refrigeration trailers and some lawnmowers, we need to do something about the exhaust. Today, we're going to take the car out for its first road test with the automatic fuel and boost control system. Now, off camera, I did spend a few hours putting together some software that will completely automate the engine controls, and I'm excited to see if it actually works. So let's get started. So before we take the car out on the road, I guess I should mention that we've temporarily replaced the Bridgestone E22 low rolling resistant tires with generic tires. Actually, the Bridgestone tires ended up on the other Honda Insight, so I could do a real-world testing on the tires. So far, the results have been interesting, and it would appear that the E22 tires that were designed for the Honda Insight truly make a difference. In case you're wondering, on the normal car, we've gained an average of 2 miles per gallon when we swap the tires over. Very interesting indeed. Now here's something to keep in mind. Swapping the tires won't affect the speedometer on the test vehicle because on this car, we use a small armada of military-grade high-tech GPS satellites that are strategically placed in orbit around the planet in order to measure the speed of our test vehicle. And any variation in wheel size will have no effect on our data. So, in other words, our $30 GPS speedometer will still do a crappy job at measuring ground speed despite the change in tires. Today, well, the ambient temperature's in the mid to low 90s, and prior to taking the car out on the road, we aired out the interior for a few minutes, and we opened the driver's side window to provide adequate ventilation to the driver. The driver's side window will remain open because it's cruel to make the driver suffer more than he has to while driving this car. Over on the passenger seat, the Arduino-based electronic package is sorted and ready to go. Over on the dashboard, we mounted a tiny display so we can monitor the data on today's road test. The display is effectively a window into the operating system so the driver can see what part of the program is being executed under various road conditions. Here, let me show you how it works. So this data monitor is going to be used as a tool to help develop the main automation program. Currently, the fuel rack limiter and the boost valve are being controlled with a simple 4-step program based on the throttle position sensor. Right here we can see the program is in stage 1111 of the automation program. Now we still have the manual controls in place, but when this boost control knob is set to 0, it disables the manual controls and allows the Arduino to automatically control the engine. If I twist this knob clockwise past the 20% mark, well, the automatic program is now disabled and the rack limiter and boost valve are now in manual control. And we can see the mode switch from 1111 to 8888. And at this point, I can dial in the rack limiter or boost manually. Now, for most of today's tests, we'll be in automatic mode and taking notes on where the changes need to be made. Like I mentioned earlier, this is a tool to help develop the main program. Today, we're going to be running a super simple program based on the throttle position sensor. As you can see, with the TPS or throttle position sensor at 0,
we need to talk about your TPS reports.
The program is in stage 1. The display indicates 1111, so it's easier for the driver to see. The boost and rack numbers that you see probably won't make sense to most folks. The 100 means the boost valve is 100 steps from its home position. Remember, we're using stepper motors for the boost and the rack limiter, and these motors move 1 step at a time. So, at 100 steps from its home position, that translates to nearly all the boost is being vented. For the boost, the higher the number of steps means the more boost is being sent to the engine. Now onto the rack. The 196 is 196 steps from home position. Now, as it turns out, this number puts the fuel rack limiter exactly at the factory calibrated settings. So for the fuel rack limiter, the more the accelerator is pressed, well, the smaller this number will get. And what that means is the fuel rack limiter will start retracting and allowing the fuel rack to move past its factory calibrated settings. Now if I press down on the accelerator slightly more, we can see the Arduino is now executing stage 2 of the program. So basically at this stage, the boost steps went from 100 to 185, and what that's doing is it's starting to limit how much boost is being vented, and now we're feeding the engine pressurized air. But as you can see, the rack limiter didn't move at all, and that's fine. Adding boost before we add fuel is how we're trying to keep the exhaust visibly clean during acceleration. Now if I press the accelerator just a little bit more, the boost valve adds even more boost to the engine. Remember, the higher the boost steps, the more boost we send to the engine. Now at this point, the fuel rack limiter starts backing off and allowing the fuel rack to move past its factory calibrated point. Now allowing the fuel rack to move past its factory calibrated limit will result in a visibly dirty exhaust. However, since we're feeding the engine plenty of boost at this point, the extra fuel is being consumed more efficiently. Now, don't forget, this is a diesel engine and not a gasoline engine. Diesels naturally run lean and they love boost. The stuff we're doing to this engine is perfectly fine. However, on a gasoline engine, I'm afraid this scheme wouldn't work at all. Anyway, if I press down on the accelerator past 70%, as indicated by the TPS sensor, now we're sending full boost and the fuel rack limiter has backed off to 150 steps from home position. This number is a little bit iffy, but it's a good starting point for maximum power. We may actually need to back off a little bit more, but I won't know that for sure until I do some testing. So in order to visualize what's going on, another way to look at it is our basic program operates in 4 steps: idle, part throttle, mid throttle, and full throttle. This will work for today so we can gather performance data, but this basic program is less than ideal. And with the data we get today, we can rewrite the program to eliminate the steps and have an active response that's more linear. But before I can do that, first I have to validate my estimated waypoints provide generous amounts of boost and fuel while still keeping a visibly clean exhaust. Okay, let's start this contraption and see what she's got. So far, so good. Now if we look at the boost gauge, we can see at idle there's 0 boost. And if I press down on the accelerator a little bit, the boost instantly comes alive. Not too shabby. So if I get a little crazy and press down on the accelerator all the way, we get max boost instantly along with an ample supply of fuel. Now keep in mind, this engine is equipped with a governor, so it's more or less safe to mash the accelerator to the floor. Alright, let's take the car out for a ride to see how all this stuff works. Now in this test, my brother Duke will be following in the chase vehicle to keep an eye on the exhaust. If this car belches so much as a single puff of smoke, I'll be getting a phone call from the Duke. Well, right away I can tell you the car drives exactly the same as it did without all the gizmos, which is what I expected, and it's nice to have something work as expected. So far, so good. Now, at this point, I wanted to jot down a note on a slight change I want to make when I write the final program. So let's fast forward a little bit. Now I'm running the engine at the top of stage 3 where the TPS is just under 70%. I want to hold the throttle here and see how fast the car will go and how hot the exhaust gas temperatures will get. And it looks like 66 miles per hour is all she's got at the top of stage 3. Let's kick it up a notch and go to stage 4 and see what happens. So at full throttle, the car caps out at 74 miles per hour. Meh, it really should have gone a little bit faster, but that's the reason why I'm out here validating numbers today. Now over at our makeshift drag strip, we did some low power acceleration tests to verify we still had a visibly clean exhaust on the extreme low end, and again with a little bit more throttle. Now this time, we engaged Warp Factor 9 to see the effects of a hard launch with full boost and max fuel. Yeah, it'll roll a little coal, but that's significantly less than before. Of course, out in the sticks, lawnmowers of all types have access to our drag strip, and today I can say without a doubt I have the fastest lawnmower powered vehicle. Anyway, my brother Duke chased this silly car for miles and miles as I put it through all its various modes, and sure enough, the gizmos have completely eliminated any smoke from the tailpipe without affecting the performance at all. I reckon a bit of technology and some simple code can more or less fix anything if you know what you're doing. Now keep in mind the software works fine as is, but it's not optimized and I'll need to go back and rewrite the code so the gizmos are constantly making adjustments. Right now it's just 4 stages, and in the final code I'll eliminate the stages and use a formula for a linear function. And at that point I can incorporate the vehicle speed sensor to detect when the car is stopped and when the car is at cruising speed. The tachometer input, well, we may or may not need that. Overall, the system seems to work fine without any of the speed sensors, and that's why I didn't make them a major part of the software. So far, I've made the claim that the performance feels the same, and for the most part it does, but really I need to validate that, because so far all we've proved is these gizmos help with a visibly clean exhaust. Now in theory, we should also be able to tweak a little bit more power from the engine as well. Alright, let's see if these gizmos have an effect on the full throttle performance of the supercharged intercooled 719cc Kubota diesel engine. For this acceleration test, we're going to run the car at full throttle and accelerate up to 55 and 60 miles per hour. On this test, we'll be at 100% throttle, and that means we'll invoke stage 4 of the program. Now earlier in the video, I mentioned that the fuel rack number was, well, a bit iffy. Let me explain. This number is an educated guess, and it may be too conservative. The good news is, it's just a number in a program, and adjusting this number can be done with a mouse and a few keyboard inputs. You see, this number tells the fuel rack limiter to adjust the rod 150 steps from its home position, and that will block the fuel rack from moving this way. In the event 150 keeps the engine from making full power, well, we can change the number to perhaps 140, and that will tell the rack limiter to only extend 140 steps from its home position. As you can see, that opens up a space between the rod and the fuel rack, and now the fuel rack can move this way a tiny bit more, thus allowing more fuel to be injected into the engine at full throttle. Of course, the boost on this run will be 100% of what the supercharger can develop. Alright, let's see what happens. The time to beat for 0 to 55 is 20.06 seconds, and for the 0 to 60, it's 24.04 seconds. Well, that was interesting. Since I've spent a lot of time in this car, I could tell the engine went soft between 51 and 55 miles per hour. So yeah, it looks like I need to change this number in the program. Meh, that's the awesome thing about software. Anything is possible if you know how to express it in code. So any result, whether it's good or bad, is always interesting, at least for me. I always love to look at data. Now, speaking about data, I had a look at the channel analytics, and in the past few weeks it appears when I deviate from nuts and bolts to electronics and software, well, I drive away part of the audience. At least that's my interpretation of what I'm seeing. I also have to keep in mind that this time of the year a lot of folks are on vacation and enjoying the outdoors, and perhaps they just don't have time for videos. Speaking about vacations, well, I reckon now is a good time to mention that I'm off for the next 2 weeks. Well, sort of. You see, I'm a workaholic and I'll have my laptop with me so I can still write software and finish this project. Anyway, I had fun today and I hope you did as well, and I'll see you next time. Until then.